Low-cost, large-scale electricity storage is often described as a game-changer by the energy industry as the best way to manage grid fluctuations in a power-hungry world. Moment-to-moment changes in electricity supply and demand can vary drastically, challenging power grid operators who must maintain an exact supply and demand balance in real time to avoid power disruptions and blackouts. The unpredictable nature of storms, outages, and intermittent renewable energy resources like wind and solar create additional complications for grid operators.
The nation is facing some substantial new challenges for its power system, both from the new supplies of renewable energy, new more complex demand response activities, and new security challenges. So it's vital that the nation provide new solutions in R&D, particularly in energy storage, to give us a more flexible, adaptable system that we need for the future.
Researchers at the Pacific Northwest National Laboratory have developed the iron vanadium redox flow battery, a commercially viable, grid-scale storage technology that provides the energy industry with a reliable, stable, safe, and low-cost solution that can be widely deployed. The advantage of redox flow batteries is they store captured energy in the flowing electrolytes. The volume of the electrolytes can be independently increased to support storage capacity of any size. Separately, the battery power output can also be independently increased to the desired kilowatt power output level, providing the maximum flexibility and efficiency for every application. The iron vanadium redox flow battery builds upon this beneficial feature and adds many unique innovations. The most distinguishable characteristic of this next-generation redox flow battery is it limits the non-uniform transfer of ions across the battery cell separator membrane, called crossover. This new approach provides long-term energy cycling stability, overcoming major cost, operational, and performance limitations of the current generation redox flow batteries. Researchers achieve this through a design that uses a more benign chemical composition that does not corrode the separator membrane. This chemical composition allows the use of readily available microporous separators for the membrane, which reduces membrane costs by 95%, lowering overall system costs by 25%.
The advancement we made on this redox flow battery technology will allow the industry to have an option for the energy storage that is low cost, faster response, and suitable for the large-scale energy storage.
The battery is highly efficient, stable, and safe. It responds to power surges and losses in milliseconds, has far lower maintenance requirements, and can operate in broad temperature ranges from -10 degrees to 60 degrees Celsius, removing the need for active heating or cooling of the system enclosures in many parts of the world.
We at ARTHA firmly believe that this storage technology will provide grid operator the missing link that they need in managing the grid for the complexities of the load and supply and demand.
The Pacific Northwest National Laboratory's iron vanadium redox flow battery technology, helping achieve a cleaner, efficient, and more reliable energy future.
Support for development of this technology by the Pacific Northwest National Laboratory was provided by the U.S. Department of Energy Office of Electricity Energy Storage Program.